Okay, let's take a look at ionic compounds versus molecules. This topic is still in chapter 2.3. Now, an ionic compound, this is a substance that is held together by ionic bonds. Makes sense? Molecule is covalently bonded substance, a covalently bonded substance. Okay? So, ionic compounds versus molecules. Now, the reason we have a difference here is an ionic compound does not have distinct particles where one atom is bonded specifically to another atom. In an ionic compound, all the cations are attracted to all the anions. So let's take a look at this diagram. So here's sodium chloride, table salt. It's an ionic compound, and you have a sodium ion, chloride ion, sodium ion, chloride ion, chloride ion, sodium ion. And you notice the little arrows around here. That sodium ion is equally attracted to all these negative ions around it. This negative chlorine is equally attracted to all the positive charged sodiums around it. And keep in mind, this thing is not just two-dimensional like on this sheet that you're looking at or screen that you're looking at. It is three-dimensional. It is also attracted to sodiums coming out towards you and back behind it. Okay, the molecule, down here we have carbon dioxide. So this carbon is bonded to that oxygen and that oxygen. This carbon is bonded to that oxygen and that oxygen. That carbon does not have any attraction or bonding with this oxygen up here. So in a molecule, each of these carbons and two oxygens are distinct units, separate from the others. Whereas in an ionic compound, they are not. They are all each cation is interacting with all the anions around it, vice versa. Okay, and let's see. That I think we can skip over. I think we looked at that earlier. So here's our, right here's our chlorine or sodium, and so chlorine, sodium, chlorine, sodium, chlorine, sodium. So notice how they're all stacked in there forming a crystal, but this sodium is equally attracted to all the chlorines around it. That's an ionic compound. Now let's look at hydrogen bonds. Notice this is in red, meaning good chance you're going to see this on the exam. Okay, hydrogen bonds. This is a weak attraction between a hydrogen with a partial or weak positive charge and either an oxygen or a nitrogen with a partial or weak negative charge. Okay, so here we go, hydrogen bonds. So notice right here, here's a hydrogen with a positive charge and dot dot dot, meaning we have a weak attraction to this oxygen with a negative charge. Or it could be between a hydrogen and a nitrogen. So down here we see, here's a water molecule, here's another water molecule, and we have a positive charge on the hydrogens, negative charge on the oxygen. There's a weak attraction between those opposite electrical charges. That's a hydrogen bond. Likewise, this is a hydrogen bond, a weak attraction between this positive hydrogen and this negative nitrogen in this ammonia molecule. Okay, so this would be a water, that's an ammonia. Okay, so here's a diagram from your textbook. Their artwork is a little better than mine, but you notice here's our water molecule, positive charge on the hydrogen in the water. Here's the ammonia, negative charge on the nitrogen, weak attraction between those two. That is the hydrogen bond. Okay. Now these hydrogen bonds are very important in water. One water molecule is hydrogen bonded to the next water molecule. It's also important in large organic molecules like proteins and DNA. Okay, so let's look at this one. Chapter 2.4 in your textbook is on redox reactions. Now, we have what's called reduction oxidation reaction, or abbreviated redox reaction. And this redox reaction involves transfer of electrons from one substance to another. The biological importance of this is of a redox reaction is energy transfer. There's energy associated with that electron, and if you transfer the electron from one substance to another, you are transferring energy. Notice that's in red. You're likely to see it again on the test. Okay, reduction. If a substance gains electrons or hydrogens, then that's reduction. Now remember, a hydrogen atom consists of one proton and one electron, so if the hydrogen atom is transferred, the electron is transferred, and the energy with that whirling electron is transferred. So, the substance that undergoes reduction gains energy. Okay, now the way to keep this straight is think, what is the charge on an electron? It is negative. So if a substance gains electrons, it is gaining negatives. Therefore, it is being reduced. Okay, oxidation is the opposite of this. The substance loses electrons or loses hydrogen atoms, and that hydrogen atom is going to carry one electron with it. Well, remember, there's energy associated with these electrons, so a substance that loses these electrons loses energy. So the biological importance of this redox reaction is that it's a means of energy transfer. Energy is associated with that electron that is transferred. Okay, redox reactions, reduction, oxidation, these have to occur together. If one substance is reduced, the other has to be oxidized. So if one substance gains an electron, that electron didn't come out of nothingness. It came from somewhere. It had to come from another substance that had to be oxidized. Now let's take a look at water. This chapter 2.5. Water is pretty important when we talk about a living organism. 70% of the human body is water, and water is a polar substance. Water is a polar molecule, meaning that it has electrical charges on each end. And this polarity is due to the polar covalent bonds between the oxygen and the hydrogen. That pulls the electrons towards the oxygen and puts a negative charge on the oxygen end, positive charge on the hydrogen end. So here's our water molecule. There's oxygen, here's our hydrogens, and the little arrows are showing the electrons are skewed up here towards the oxygen end. Well, remember, those electrons have negative charges to them. So over here, what we're going to see is we're going to get a weak negative charge on the oxygen end, and it's going to leave a weak positive charge down here on the hydrogen end. Remember, especially with hydrogen, it just had the one electron, and if that's skewed up here towards the oxygen, that leaves a bare proton, bare positive charge sticking out down here. So this little diagram right here showing the polar nature of water, you probably want to be familiar with that. You will probably be asked to identify that the correct distribution of the charges on that water molecule. Okay, polarity, these charges, causes water to be a fantastic solvent. Now we've got the terms solvent, solute, and solution. Solvent is a material in which substances dissolve, thus water. Solute is a dissolved substance, so like salt, sugar, but it could also be gases, could be a solute. They could be dissolved. And the solution is the whole thing, the solvent plus the solute. Okay, so here's our little salt shaker. There's the crystals of salt falling into the water down here. Sodium chloride, that's a chemical name for table salt. And when this hits the water, that sodium chloride splits into its sodium ion and chloride ion. It's cation and anion. And when this dissolves, notice the water molecules, the electrical charges on the water molecules will interact with the electrical charge on that ion, and the sodium ion is going to be surrounded by water molecules oriented in this direction with the negative oxygen end pointed towards that strong positive charge on the sodium. And the chloride down here, that's just chloride's just a name for negative charge chlorine. It is surrounded by water molecules oriented in the opposite direction, where they have that positive charge oriented towards the strong negative on that chlorine anion or chloride. Okay. Now there's your textbook showing the same thing. Just their artwork is a little bit better than mine. Okay. Okay, soluble substances. This is substances that are soluble in water, have polar covalent bonds. So that would be like sugar, or they are ionic compounds. Either way, they have electrical charges. So they are hydrophilic, water loving. And if it's soluble in water, it has electrical charges to interact with charges on the water. Okay, substances that are not water soluble have nonpolar covalent bonds, like fat or oil. These are hydrophobic, water fearing or water hating. And these do not have electrical charges to interact with charges on the water. Okay, so oil and water do not interact with each other. The two molecules just kind of ignore each other, and then they separate based on their density. Now, the other thing that we get, let's go back here for just a second. Remember, water is polar. So we said water is polar. It has electrical charges on the water. And here's the polar nature of water, electrical charge on either end. And this polarity causes water to be a fantastic solvent. Let's look at that. And then the other thing is this polarity causes water to form hydrogen bonds. So here's our example of the hydrogen bonding. A weak attraction between this weak positive on one water molecule and the weak negative on the oxygen of another water molecule. And so in a body of water, or in water in your body, one water molecule is attached to the other water molecules around it. Each water molecule can form up to 4 hydrogen bonds around itself. Okay? And so there's a diagram from your textbook, and once again showing the same thing as this, just a little bit better artwork. Okay, because of these hydrogen bonds, water has quite a few unique properties that we just don't see in other materials on Earth. And these unique properties are due to the hydrogen bonds. Okay, so let's take a look at those unique properties in another video. We'll stop here. Okay.